In this video, we'll look at a proof of the Pythagorean theorem that was first discovered by the 20th President of the United States, James Garfield. Now, to give you a little background information about Garfield, who was a unique man, as you'll see, he was, among other things, a teacher, a principal, Ohio State senator, a Union Army general, a congressman, a U.S. senator, and finally president for 200 days in 1981 until he was unfortunately assassinated. But in 1876, Garfield developed this proof of the Pythagorean theorem, and for a short time it united both houses of Congress, both parties. He has a famous quote, "We think it's something on which the members of both houses can unite without distinction of party." Imagine that, but as you'll see, there wasn't much room for argument. So let's get into how he did it. Garfield began his proof by constructing a right triangle. He did this by constructing a line segment and then constructing a perpendicular to this line segment. It's important to note that this angle is 90 degrees, and we know that because we have this line and this perpendicular line. Finally, he finished off his right triangle by adding in another segment, just like so, and you can see that we have this right triangle. Let's go ahead and label the side lengths. We'll label the longest side C, the shortest side A, and this other side B. Garfield then began constructing a right triangle congruent to the first. He did this by constructing a circle with radius equal to length C, centered at this point. This looks like this. Then he constructed a perpendicular line at the center of the circle. So this point with this line, and you'll notice what we get is a second radius. This segment right here from the circle to the center point is also equal to length C. So copy that and label this length C. Garfield then constructed a perpendicular line at the intersection of the circle and the second radius, so right here, with this line right here. So we can construct that perpendicular. And what you can see is that the second right triangle is now visible. Let's go ahead and begin cleaning up what we have by hiding some of our constructions and then filling in the other segments. So we have that intersection point, and now I'm going to begin hiding some of our constructions. So this line, our circle, basically all of the lines, and we'll leave those in there. Let's fill in the rest. This right here is a segment. This right here, segment. Here, segment, and this final segment. Let's also label some of these side lengths. We could go ahead and prove that these two triangles are congruent, but in this video we won't. This length is B, it's congruent to this length B, and finally this is also congruent to the other length A. Garfield's final step was to draw a segment in order to create a trapezoid made up of three right triangles. He drew a segment from this point to this point, and you can see that what we're left with is a trapezoid, base B and A with height BA, made up of three triangles. Let's go ahead and label these triangles. Call this first triangle, triangle X, this congruent triangle, Y, and then our third triangle, Z. Now let's add some color to better show that triangle Y and triangle X are congruent. There we go. Now notice that there are at least two ways to view the area of this larger quadrilateral. we can view the area of this quadrilateral as the sum of the areas of the smaller triangles. In other words, the area of x plus the area of y plus the area of z. Symbolically, that looks like this. The area of x, the area of y, plus the area of z. But Garfield noticed that there was a second way to view the area of this larger quadrilateral. He viewed the area as a trapezoid. You can see that if we take away these individual triangles, x, y, and z, we have a trapezoid with bases b and a, and height equal to b plus a. His proof follows from this equation. Garfield's proof comes from substituting values into this equation. Let's go ahead and substitute some values in. First of all, the area of triangle x. Remember, the area of a triangle is 1/2 base times height. So the area of triangle x is 1/2 AB plus, now the area of triangle y is the same because those triangles are congruent, plus 1/2 AB plus, and now the area of triangle z, the base is c, the height is c. We know this is a right angle, so we can write the area of that as 1/2 c times c, or c squared. And we know that this area is equal to the area of this trapezoid. Now the area of a trapezoid is base 1 plus base 2 divided by 2. Another way to write that is 1/2 b plus a times the height. Now the height is b plus a. So we have another b plus a. Let's go ahead and simplify what we have. Well, let's FOIL this out, distribute the 1/2, and then multiply b plus a times b plus a. When we do that, we get 1/2 b squared plus 1/2 ab plus 1/2 ab plus 1/2 a squared. And on this other side, we'll leave it as is for now. We know that this is equal to 1/2 ab plus 1/2 ab plus 1/2 c squared. And again, we know that these two areas are equal. Now what we can notice at this point is that we have 1/2 ab's on both sides. We have a 1/2 ab here, a 1/2 ab here, so we can cancel them, and there's two other 1/2 ab's. When we reduce, what we're beginning to get is the Pythagorean theorem as we know it. 1/2 c squared is equal to 1/2 b squared plus 1/2 a squared. And then if we multiply both by 2, we end up with the Pythagorean theorem, or c squared is equal to, that's a b squared plus a squared. And there it is. That's how Garfield proved the Pythagorean theorem. And for a moment, united both parties. There clearly was no room for argument.